we'd sort of maybe take some of the details for granted. But it's well within everyone's ability to do this. So let me just set it up and tell you what the answer is. So we deal in 2 dimensions. It's pointed out that in medical EIT, anyone who is 2-dimensional has already been squashed and there's no diagnostic difficulty in finding out what's wrong with them. But what I actually mean, is what I actually have in mind, is a cylindrical tank where the electrodes run the whole length of the object, and the things that I put in are long cylindrical objects. So there's no variation in anything in the, say, Z direction upwards, in which case it does actually reduce to 2D. So that's really the only case that you get for 2D, but it's easy to calculate in 2D. So, so we take that in mind. And so we have a circular dish, we have a concentric anomaly, in other words, a round thing in the middle, and we make the conductivity, whatever I've said on the board. Right, so this is radius rho. As you can see from my picture, it's right in the middle. And inside rho, we have a conductivity of sigma is A1, and outside it's A0. And the radius is a unit disk to make things simpler. So it's probably best to work it out for a unit disk and then just scale it. Okay, so what happens here? Well, you can solve this by separating variables. In other words, use polar coordinates. So u is a function of r and theta. Let me remind you roughly how the procedure works. You look for solutions that are a product of some function of r and some function of theta. And that's called separation of variables. And when you do those separation of variables, you find that you have solutions that are of the form r to the k e to the I k theta. So, in other words, when you separate variables, you get an ordinary differential equation for r, an ordinary differential equation for theta. The one for theta is just simple harmonic motion. And you find that this number k has to be an integer. Actually, so any integer, positive or negative. And then you get a little bit clever about this. You realise that negative powers are okay in this area where r is non-zero. And so actually what you have to do is you have to work out this part, solution in this part, a solution in this part, and then you have to match the boundary conditions. So actually at this interface, both the voltage and the current have to agree, right? So even though the conductivity jumps. And that couples the 2 equations together. But the interesting thing about this is that for the outside solution, because r is bigger than rho, you can have a negative power, but for the inside bit you can only have positive powers. And so that's actually the subtlety in doing it. And I say e to the I k theta, it's slightly easier to deal with. Of course, I mean just cos k theta and sine k theta. And what you do is when you get a sum of these to make an arbitrary solution, the coefficients in that sum have to be such that the answer is real, right? So it's easier to do it via complex numbers. Slightly easier. So you know, we can kind of keep everything complex as long as we just know how to put in real voltage or real current and get a real voltage or current out. Okay, so that's the technology of how we do separation of variables, and the equation we get to solve is to match the boundary conditions at r equals rho. And what we find is that if you write, let's start with the voltage, u of 1 theta, that's the voltage at the boundary as a function of theta, okay? So that's the Dirichlet boundary data. If you write that as a sum of ck e to the I k theta k equals minus infinity to infinity, then that's a complex Fourier series. I could do a real Fourier series, but then I have to write more. I have to write A's and AK's and BK's, right? And of course it's periodic, so I can period 2 pi, so I can do that. So that's any voltage that we care to put in that has a Fourier series. And then what I want to do is to say, if I put in that voltage, what current would I get? And then I can say what happens with EIT. We either apply voltage and measure current, or we apply current and measure voltage. In any case, we end up knowing both of them. And of course, the idea of EIT would be to find the conductivity. In this case, the radius and A1 and A2. Well, it turns out that this is very easy to do, and perhaps it might be best if I said, okay, so the current density sigma du by d, well, R is the normal, okay, at 1 theta. Let me write that as another series. Let me call that C tilde k, e to the I k theta. Okay. So over k. So they both have a Fourier series. One's called ck. So the Fourier coefficient is called ck and ck tilde. And the nice thing about this is that the current density, ck, its kth Fourier coefficient, turns out to be, I've written it as k instead of n here, so just have to translate, absolute value of k times 1 plus mu, for our remote audience, I'm copying this off the slide, at least I was until the projector comes out. 1 minus mu sorry, that's not 2k, that's absolute value. It's 2, absolute value, 2k. Right, I don't need the ETIK. Times ck. So in other words, for each frequency component, the k frequency that you put in as a voltage, the current comes out like this. Let me just simplify this. I have to say what mu is. Mu is a kind of fairly sensible kind of ratio, the difference over the sum. Okay, so let's first of all think, well, what if A1 was equal to A0, so there isn't any anomaly there? Mu is 0, and so ck tilde is just k times ck. What does that mean? Well, if you get a Fourier series and multiply each frequency component by well, say I times k, that's called differentiating, right? That's how you differentiate Fourier series. E to the ik, differentiate, the ik comes down. So multiplying by frequency is something a bit like differentiating. Now when we go from voltage on the boundary to the normal derivative, it is a derivative, but it goes via solving the PDE and then differentiating in the normal direction. So just to notice here, if you don't have any anomaly, the relationship between the voltage and the current density is multiplied by absolute value of frequency. That's almost like you differentiated it. I mean, certainly in terms of smoothness, so the decay of the Fourier coefficient measures how smooth the function is. If we differentiate, it makes it less smooth, and it multiplies the higher frequencies by a bigger number, I times k, right? So we've made the higher frequencies bigger. It's made it less smooth. In a similar way to differentiating, but not exactly, because it's absolute value. So the plus and minus k components are both multiplied by absolute k. So it's not exactly a derivative. It's very much like a derivative, and it would certainly look like, you know, much more jagged, right? The current is more jagged than voltage. Okay, so with that in mind, what effect does our anomaly have? Well, here it is. And you might look at that and, I mean, so this is a nice simple case that we can solve. And you might ask yourself, how easy would it be to find mu? That's not a 4, that's 2 times absolute value. How easy would it be to find rho and mu from this? Well, I think you can see that it's a kind of higher order effect compared to, the big thing that's going on is that multiply the absolute value of k. And actually, if you look at the Fourier series of current and voltage, and you do something inside, not touching the boundary, you'll always see this absolute value of k comes out. And then there's some stuff that's a minor change to it. That's actually why EIT is so hard. If you make a change in the conductivity interior, and I could have modified this so I said, well, it's background here and mess it up, in some other way here, it would be quite similar, that the dominant effect, the frequency components, is just this absolute value of k, which as long as you don't change the conductivity at the boundary, you'll get that. And so we have to look in here to find mu and rho, and I think, well, we could probably find a way to solve it. If we knew that the system was like that, it was a concentric anomaly. But rho is a number less than 1, and so it's 1 plus something less than 1 raised to higher and higher powers. So very quickly this gets quite a negligible effect. So the lower frequencies are more affected by it, the lower spatial frequencies of current pattern, and the higher spatial frequencies, really much less affected. And that corresponds to lower spatial frequencies, putting in a voltage that was shaped like cos theta, the current would sort of flow straight across, whereas if you put in cos 10 theta, then the current would be rippling in and out of the boundary, and not really getting anywhere near the middle. So it wouldn't be telling you a lot about what's going on in the middle. So there's a wealth of information in this very simple example. Not only that, but with a little bit of a conformal mapping, you can even move this around to sort of change the coordinates. So you can get one blob anywhere and solve it completely. So again, it's not so surprising that fish were able to locate one object. It's kind of almost write down a formula to do it. So you could presumably implement that in a neural network or a fish brain, right? Indeed, in geophysics, if you want to think of a two-dimensional geophysical problem, you would have to have very long electrodes running along ground. Then you can take a conformal mapping that maps this disk to a half space, and then you can use a similar kind of analysis for that. So that kind of concludes my discussion of the forward problem, and I'm not sure that it's worth going through the details of this unless you've done the PDE course of separation of variables, and maybe it's worth doing once. But it's more fun to write a little program where you put in Fourier coefficients and then change mu and rho and see what it does to it. Because then you can develop an intuition about how hard EIT is, and you can even ask questions about, if I can measure to a certain accuracy, what size of blob with what contrast could I find? Kind of fundamental limitations of EIT with that. So not so much deriving, but playing with this example is very instructive for you. Okay.